In problem 74, we want to use the alternative form of the derivative to find the derivative at x equals c if it exists. And the alternative form of the derivative of g of x would be the limit as x approaches c of f of x minus f of c over x minus c. Now in this case, if g of x is x times the quantity x minus 1, we can multiply that out to be x squared minus x. And c is equal to 1, and since this is a quadratic function, it's a polynomial, we know that it is continuous and differentiable everywhere. So the derivative has to exist at x equals 1. So we want f of x, which is just x squared minus x, then minus f of c, that's f of 1, and we have 1 minus 1, and that's simply 0. And we'll divide that by x minus 1, and so this becomes a typical limit that we've solved many times. We're going to factor and cancel here. So we have x times x minus 1 divided by x minus 1. The x minus 1's will cancel, and that simply leaves x. And here we can just do direct substitution, put the x equals 1 in for x, and we get a value of 1. And so this form is pretty easy to use when we're just looking for the derivative at a particular point. That's why this function is often called the derivative at a point, or this alternative form is called the derivative at a point. And we'll go on to the next problem. And we'll see how much simpler this type of problem becomes. Again, we want to use the alternative form of the limit definition to find the derivative of x cubed plus 6x when x is equal to 2 or c is equal to 2. And so that means we want f prime of 2, and that's the limit as x approaches 2 of f of x minus f of 2 over x minus 2. And now we're ready to plug in. F of x is just x cubed plus 6x, then minus f of 2. F of 2 is 2 cubed, which is 8, plus 6 times 2, which is 12, so that's minus 20. And that's all divided by x minus 2. Now we can't factor this directly, but since we're trying to cancel with x minus 2 in the denominator, we may try a synthetic division with 2 as the root. So we'd have 1 for the x cubed coefficient, we have 0 for x squared coefficient, 6 for the x, and minus 20 for the constant. Bring down the 1 times 2, add that to the 0, multiply by 2, 6 and 4 is 10, times 2 is 20, and we get a remainder of 0, which means that 2 is a root, and that leaves us with limit as x approaches 2 of x minus 2 times x squared plus 2x plus 10. Divided by x minus 2, the x minus 2's cancel, and now we're simply plugging in x equals 2 into x squared plus 2x plus 10, and so that's 4 plus 4 is 8 plus 10 is 18. And that is the derivative at x equals 2. Again, you can see how much simpler that was than doing this, especially with a cubic function, using the limit definition, the formal definition of the limit of the derivative. And we'll go on to problem number 80. In problem number 80, we want to try the same exact thing. We want g prime of negative 3. Now I know by looking at this that we're going to have a problem. The parent function here is x to the 1/3 or cube root of x. And cube root of x has a vertical tangent at x equals 0. Well, x plus 3 to the 1/3 is a horizontal shift 3 units to the left. And so that'll have a vertical tangent at x equals negative 3. And a vertical tangent, at a vertical tangent, the derivative doesn't exist because the slope of a vertical line is undefined. But let's see how the math carries out. We have the limit as x approaches f of x minus f of negative 3 over x minus negative 3. So f of x is x plus 3 to the 1/3. At negative 3, negative 3 plus 3 is 0, so f of negative 3 is 0, and that's divided by x plus 3. And since we have an x plus 3 in the numerator, we can write x plus 3 in the denominator as x plus 3 to the 3/3, which is the same as the first power. And we divide two numbers with the same base, we subtract the exponents, we get x plus 3 to the negative 2/3, which is 1 over x plus 3 to the 1/3. When x approaches negative 3, the limit doesn't exist, and that verifies that there's a vertical tangent